okay, let's assume this is a 5 kilobyte file. So you have 4 partitions, and this example, what we have seen is that, say assume that this particular bank has a total of 3 accounts. That's all they have. The entire bank has 3 accounts, and they wanted to find the end of the balance for each of the account. Okay? So the end of the balance, what they're going to do is that they're going to sum up all the withdrawal and the credits, and then the final net amount is your balance. Okay? That's all they're going to do. Literally, they're just going to do a sum. Okay? But you notice that throughout the day there will be this is a transaction log, right? This is for example, they pulled this file out of ATM transactions. So all the transactions that you do in ATM, it just gets stored in a file, and they're going to process that. Okay? So throughout the day, these people come and then they withdraw. These 3 account holders, they come and withdraw, they deposit, they withdraw, they deposit. They do a whole lot of things against the thing. So you don't have control over which guy actually does which thing at what time. Right? So this particular file has a mix of partition 1 could have account 1 doing certain transactions, and followed by account 2 and account 3 or whatnot and so forth. But the idea is that you wanted to find a sum per account, which means that you have to pull out all the account 1 related stuff, and then you have to pull out account 2 related stuff and 3 related stuff. You have to split them out. Okay, that's the idea. So they use a function called map. Okay. How many of you remember set theory? Set theory. Anyone? Okay, set theory. The map. Not actually math. I mean, it's like bullshit. In set theory, you have the sets, right? The set. Probably I'm not pronouncing it properly. Okay, so you have set A is set A, set B, and then say this would be a universe and whatnot and stuff. Anyone? Okay, never mind. So the point is that say assume that you have this numbers, right? 1, 2, 3 is your set, okay? Is your entire set. And then assume that the B set has 2, 4, and 6. Okay? So this is your set A and set B. Now, what do you think happens here? What is the function that happens here? Exactly. It is f of x is just actually times 2, correct? That is what happens here. So in order to map your set A to set B, you're applying a function which is just times 2. That's what you're doing. Okay? So what Google did was that it took this idea around it's just a very simple idea if you look at it. It took this idea and then said that all I need to do for processing this one is that if I need to split it up, I'll take this particular data set and then apply a function on top of it to give me few data sets. Okay? Few data sets. In this case, what it does is that it just takes a big file and then creates 3 small files out of it. Okay? And that is what this map function does. So the partition 1, the 128 MB gets ingested into map function, and then this map function, all it does is that it's going to split the file into 3 files according to the respective accounts. When I say files, they are literally files. They are literally text files which is written on your local machine itself. Okay? So this is machine 1, 2, and 3, and 4. Because I've already told. When I say machine 1, 2, and 3, and 4, what do you think in terms of yarn that means? What does machine 1, 2, and 3, and 4 mean in yarn? It's node manager, exactly. So these are just node managers because the computation runs on node manager, right? There are 4 node managers, wherein because each of the node manager is just going to process one single partition. Okay. We'll just assume that one single node manager handles. There are cases wherein several computations can run within the same node manager. We'll come to that later. But for now, we can safely assume that one single node manager just handles one single partition. So the node manager 1 takes it, and then it's the map function, whatever implementation there is, at the end of the map function literally writes 3 files in the local machine. Okay? That's it. In the same way, the partition 2 happens, 3 files. And you can notice that the size of the transactions It could vary because based on whatever partitions it's choosing. So partition 3 has a lot of transactions for account 2 than account 1. Something like that. So you get the rough idea. I mean, each thing does it. So what you have done now is that you take the data, and then once you have done this splitting, which is done by map function. Map function can do a whole lot of other things, but once you split the file, the next thing is that you need to bring all the account 1 related files into one single machine, because you're going to sum them up, right? So in this example, say assume that you wanted to pull in account 1 from several different machines into one single machine. So this particular function called reduce, this particular function is called reduce. And in order to explain reduce, I'll assume that let's take an example of let's take the example of dominoes. The dominoes, you have a bunch of dominoes lined up, and then you do one, you just what do you call it? Move one, the first one just does a fold. It just does something like that. Let's take that example in the real world scenario. Assume that you want to, each of you have a number, okay? Each of you imagine a number, and I wanted to find what is the sum of the numbers. Okay? So this person has the number 3 in mind. The next person has the number 5 in mind. Next person 9 in mind, whatever it is. But I wanted to find the sum of all the numbers. So the easiest way, one of the easiest ways that you could do is that, and each of them has a card which has a number written in there. Whatever they have in the mind, they will write the number in the card. Okay. So he has written 3. Now what he's going to do is that he's going to pass that card to the next person. Okay. And she has a number 5 in the mind. What she would do is that she would take the 3 and then she would scratch the 3 and then add her number to the card and then say 5 plus 3 is 8, and then pass the 8 to the next person. Okay. So and then the next person takes the 8, scratches the 8, and then she adds the number 9 in her mind into 8, and then puts a total of 17. And then she passes on. So this is called reduction. So what they are actually doing is that they're taking several numbers. So this is in this example 3, 5, 9. What they're doing is that they're taking this number, they're adding it up. They say 3 plus 8 is 3 plus 5 is 8, and then you can scratch this number because 8 actually handles both 3 and 5. And then this goes there, 8 plus 9 becomes 17, and then you can scratch these two. It's called reduction. So this is the same way you do dominoes, right? Where you have the first one. Once the first one falls, the second one takes that ownership and then keeps on propagating. So this comes from a branch of not only mathematics, but it comes from something called as a functional programming. Okay? So you just reduce a value into one thing. So map is always one-to-one mapping. So for every single source, you'll have one equivalent in the target. You don't lose any values. In this example, you had several accounts. So the sum of all these values within the account, you're not losing any of them. You're not reducing the scope of any of them. So it's called mapping, one-to-one mapping. Reduction actually reduces multiple values into one. In this example, we saw sum, which is totaling the values into one. In which case, you're reducing the value by sum. You can do multiplication, or you can do whatever you like. I mean, you can do several other functions in reduction. Okay? In this case, what you're doing is just summing. Okay? So you're taking all these values from different accounts, you're consolidating them into one single value, actually. This is not the entire block, it's just one single value, just number, that's it. And the same way happens here. And finally, you write that value into HDFS. That's how the typical old world map reduce operation happens. Do we need to know this? I mean, actually we don't, because we don't do this anymore. And the reason why we don't do this is because of this. So every single step of map reduce, you're writing into a file. And this will be taken by the next map reduce program, and then reading from the file. And if there is one thing that you need to carry out of the entire discussion that happened in the 10 minutes, is that writing to local machine or writing to file system is the most expensive operation in a distributed computation. Okay? the reason is that CPU is fast, memory is fast, and storage is also reasonably okay, but network is the single most slowest thing in your cluster. A network is, if you look at all the metrics, amount of progress that we have done in the past 10 or 20 years, network speed is the slowest of the lot. So you have to be really careful about how much time you are spending writing the file to disk. Okay? And in the Hadoop or whatever Hadoop world, what they call these writing to local files and transferring the file to a next machine for processing is called shuffle. Okay? So if you look up network transfer is slow in your Google, it won't return much results. But the moment you say how to reduce shuffles, there's a shitload of results that come out. Okay? And the reason is that shuffle is it's a crime against writing distributed programs. That's all you need to know. And what is that you get out of Spark is that Spark does all these intermediate computations in memory. That's the single most reason why you use Spark. Okay. So now the moment we are going to look into Spark in detail, you just need to know that Spark does a lot of these computations in memory as much as possible. So when there is a new computation which is coming in, what it does is that the older job would just put that in memory, and even in memory it's replicated. So the next machine which comes in, it just uses the data in memory and then proceeds with that. It does not write files to the local machine. That is the single most thing you need to know why you're learning Spark. And it's not only Spark, all the modern frameworks, the big data processing frameworks, there's something called the Google Bean, there's something called as a Flink, Apache Flink, and there is a CO, there's a whole lot of frameworks which does the same, which gets inspired by Spark and then has done this implementation. I mean, whatever frameworks that you choose, if you are deciding in favor of a framework which writes files to local machine for every single stage, I think you should reconsider the framework itself. That's the bottom line. Okay. All right. Cool. Let's go back. So in this in this session, I think we can take a break after like 15 minutes maybe. In this session, what we're going to cover is that we're going to look at Spark in detail. In the morning, we were looking at data frames. Probably we'll have a quick look at it at the end of what RDD is. And then we'll look at what Spark session is and Spark context is. These are just fancy words for your entry into a Spark program. The first thing that you open up a Spark program, the first thing that you create at the top of your program is creating a Spark session. Spark session is simply at an entry point if you're writing a Spark jobs. That's all it is. Spark context, you would, that's the older version of using your Spark, writing a Spark job. We don't use that anymore, but sometimes it comes in handy, especially when you're dealing with primitive constructs like RDD. You'll see what RDD is in a short while. Okay? We'll look at what RDD is and then write effective programs or whatever it is. Okay. So most of the time that what we'll be spending the time on is for the rest of the day is on demos. We'll be looking at in live how you write Spark programs, and then we'll come back to the slides and then see if you have missed out anything, and then we'll cover it up. Okay. So, yeah.
Machine 5, 6, 7 is there.
Yes.
Same like node manager?
Yeah, it's a node manager. It's a different node, different physical machine.
So it can be, node manager can be more as compared to the data node, right?
Typically, you run node managers on all the machines wherein you run data nodes. So in this cluster, there are 7 machines.
It's not necessary that it should be equal, right?
It should not be. It need not be equal. Need not be equal. So sometimes what you do is that, say, for example, if you're running something like TensorFlow, or which requires, or any computation which requires intense GPU operations, you typically don't store your data inside machines which has GPU computations, right? So what you do is that you just have a separate set of machines which runs, which has GPU unit, and then you run a GPU computation on top of it. Your data gets shipped into that thing, because you know for a fact when you're running a computation of GPU, your data transfer is the least of the problem, because you're using GPU because the computation is going to be intense. So
in that case, computation machine should be higher memory than the storage machine, right? suppose the storage machine is 128 MB,
Yeah.
then the computation machine should be 256 MB.
Actually, no. So you don't typically. So this is an exception which I'm saying about GPUs. Typically, your storage and computation machines are the same.
Then so you are going to take the data from the storage location.
Yes.
That will be 128 MB.
Yes.
For the processing unit, we should have some memory, right? So it should be a more.
No, actually, you just have one machine because you can't afford to have so many machines separate for storage and computation. You just have one machine. If you look at how much of memory requirements is needed for data, you're right that we don't need a lot of data, but all you need is storage, correct? So there is nothing which is stopping us from having one single machine which has a lot of storage and a lot of memory, and in which case you can run both data node and node manager on the same machine, correct? So you can reuse the same. And that is the whole point of bringing your data, your computation to the node, because if your data is local, then you can run the computation on the same machine as a data node. You don't generally have separate machines for data.
Why here extra machine 6 and machine 7 is there? Because you did the computation there, reduced all the sum of the account data came in the reduced.
Yeah.
We have extra machine 6 and machine 7.
No, this is just an example. This is just an example. Ideally, this rest of the reduce operations could be run in M1, M2 as well. Just an example. Please don't take it. Yeah.
So check this M1, M7.
Yeah.
Is that in the HDFS or in the
Is in the HDFS already? No. All these work on big data, right? All these are on the cluster itself.
So M1 to M7.
Yeah, M7. Yeah, all of them are. Yes. No, I didn't get that. The Spark will do everything in memory. So what we'll do is that this transfer that you're doing may not happen all the time. It need not happen all the time. So especially what happens is that, say, in this example, let's take this example, right? So you're doing a first level of, let's take a solid example wherein you have a bunch of paragraphs. You have a bunch of text which is there, and then you wanted to do a word count. Okay? So you wanted to analyze which word, frequency of the words in that paragraph. Okay? You wanted to figure out how many words are there in this paragraph, and then you wanted to count each word as well. The first step that you would do is that you take the paragraphs, but you wanted to pick up the words out of it, right? So you're going to tokenize based on a space, right? So you pick up the words, and then the next thing that you would probably do is that you're going to maybe lowercase the words, okay? So that the uppercase and lowercase is all equalized and stuff. So in this world, what would happen is that the first step that you're going to do is that you're going to split the paragraph into words. That's the first map operation. Okay? And then the second thing is that you're going to do a lowercase of all the words. That's the second map operation. And then say, for example, the next thing is that you're going to assign say some value to it. And there could be subsequent operations before you actually reduce all the words into a single count, right? All these map operations, if you're going to write a Hadoop job, between all these map operations, you will be writing to a file, and then you'll be writing to a file. And that is exactly what you wanted to avoid. In terms of Spark, what it does is that it looks at your job, and then joins all the map operations into one single function by itself. It takes your program, it rewrites your program, and then combines all the functions into one single thing, and runs everything in memory. So it can work on it. So that's the advantage of Spark. Any questions? All right, excellent. I think 3 is a break. Okay, half an hour more.
So for like aggregating functions like calculating variance and all these kind of things, Spark cannot do it, right?
It can. We'll be looking at it shortly as well. Yeah, you can do everything. And one more thing which I wanted to point out is that in terms of Hadoop, Hadoop MapReduce, we just have 2 functions. One is map and one is reduce. And those are the only 2 functions which is available in the entire framework. And whatever computation you're going to do, say you're going to do k-means clustering, or say you're going to loop through the entire thing, there's a whole lot of computation that you can do with data, right? And everything has to be fit into these 2 functions. And that is a problem. In terms of Spark, you have a richer set of functions which you can choose from as well. Yes, aggregate is possible. Yes. All right, probably we'll take a break and then we come back.